Hey guys, this is Mr. Moog. I'm going to go ahead and take you through a lesson on Taylor polynomials and then also we're going to use those to approximate values of functions. For us, you can find that in Unit 8, Day 10 on Schoology. For College Board, they're going to reference this as 10.11. So that's where you can find all that information there. So going to take you through some notes, and then I'll take you through 4 different examples of working with Taylor polynomials. So the first thing to know is Taylor polynomials typically has this formula that we're talking about here. The formula is some polynomial expression, so it's just x's with exponents on them with coefficients in front of that. So we call it p to represent a polynomial. Sub k represents what degree you have on the polynomial. P sub k of x equals the sum of the terms created by this. This thing right here is the real definition of a Taylor polynomial. It's the nth derivative evaluated at c times x minus c to the n divided by n factorial. So this is the key right here. For anything Taylor, you should really be looking at that piece right there. There is one thing we learned in class is that Maclaurin is something similar, and I think I just spelled that wrong. I think there's an A in there. Is when C equals 0. So something important here to talk about is what this C actually is. C is the center, and you might be refreshed when I say center there as to what the center actually is. Center just means where the polynomial matches the original. So what that means is Taylor polynomials essentially are taking some function, I'm going to call it f of x, and we're going to say it's approximately equal to p sub k of x. So this function could be something like e to the x. And we could say that e to the x is approximately equal to 1 plus x squared over 2 plus x to the third over 6 plus x to the fourth over 24 plus ... That's the idea of a Taylor polynomial. We're specifically taking a real function thing, something that exists, and then writing it as a polynomial with x's and powers on those x's. So that center means that if we're evaluating it being the polynomial, close to or at the center there, it will actually give us a real approximation. It'll be accurate there. The further away from the center we get, the less accurate our approximation is there. So the main thing to know is this formula and then what it's actually talking about there. So something that's unique in Taylor polynomials is we're going to have, and I'll change my color here, we're going to have x's in it. This is a power series essentially. Granted, you're not going to be asked questions about general power series. You're only going to be asked questions about Taylor or Maclaurin. And usually they'll just say Taylor centered at C, or just say around or about C. So they might not even say Maclaurin, so you don't necessarily even need to associate the two, but they do go together. Maclaurin is a specific Taylor. So one thing to help that sink in a little bit is these graphs that I have down here. So graphical understanding is super important here. There's going to be lots of representations on the actual exam this year, so it's important to know how you can connect different things. So first thing I have here is a graph of sine. So y equals sine x. It's just a rough graph. And if I just drew in a tangent line at 0, it would look like this blue line right here. Basically just y equals x, because the tangent or the slope at that point right there is 1, so the tangent line would be y equals x. If we're going to just keep extending that, you can see right here my third degree polynomial that would represent something similar to sine is x minus x to the third over 6. So what that would actually look like is a negative cubic. So it's going to go through 0, 0 still, but it's actually going to look something like that blue right there, which you can see still approximates sine kind of in this box right here. So within that box, we're still pretty accurate to sine. Once we get outside, this point over here and this point over here don't really match at all. So it's not super helpful beyond that center there. But Taylor polynomials are really awesome because the more terms you add, so you can see my green over here, I have a 5th degree polynomial. You can see it's x minus x to the 3rd over 6 plus x to the 5th over 120. So really I'm just putting more and more terms on there. I am going to get more and more accurate as we move along. Sorry for my arm there. But that is going to be a 5th powered polynomial, and it's positive, so it's going to end like that, essentially. And you can see that our box of accuracy has gotten bigger. Before it was this little rectangle over here. Now my box has gotten bigger into where I'm accurate. Ultimately, if I made a polynomial that had infinite degree on it, which isn't necessarily a possibility, but when we use series, we can talk about infinity, like you can see right here. My polynomial would essentially just be sine. And so that's the idea of Taylor polynomials graphically. One thing to note is that derivatives and integrals might show up in terms of their Taylor polynomials. So important thing to note is that if they're talking about some function f of x, and we're going to represent it with p of x, and then that p of x is some polynomial, if they ask us about, say, g of x, and they say g of x is the integral of f of x, then really the connection we can make is that we can just essentially integrate that power series, that polynomial. So whatever connections the problem makes, we might not know anything about f of x, but we do know that we can approximate things using p of x. So if they've given us a relationship that involves an integral or derivative for Taylor polynomials, we can just go ahead and use the polynomial itself. So you got to know the first and second fundamental theorems of calculus in order to be able to actually apply this accordingly. So making the connection that f would be the integral there to g of x, and then just integrating that polynomial would be the important thing to know there. So integrals and derivatives don't actually have to be that hard, especially because it's just a power rule. So when you do the power rule, it's just either n x to the n minus 1 for deriv. Integral, it's just x to the n plus 1 divided by n plus 1. So power rule, not pretty straightforward there. The last thing that I wanted to note for you is things that we learned in relation to this that aren't necessarily going to be on the exam before. And that's the radius and interval of convergence here. Those are the two main ones. One thing, they might reference it, but the question won't be about radius or interval of convergence. So it might show up in the question, but it won't be asking you to find it. They might just mention it. And just to show you, remind you as to what that is, the box in which I'm accurate, that's the radius of convergence. The interval would be the specific numbers there. So radius is how far from the actual center. Interval is all the range there. And then the other thing that they might reference is general power series, but they won't ask you questions that aren't Taylor series, essentially. So they're going to be using the formula that we mentioned at the very beginning. They won't just ask you something generally that has a specific rule or has no rule whatsoever. So know them, but you don't necessarily need to use them on this year's AP exam. So now that we've talked through the notes, let's actually get into some problems here. So my first example says the function f satisfies the equation f prime of x equals f of x plus 1 and f of 0 equals 2. The Taylor series for f about x equals 0 converges to f of x for all x. Find the 4th degree Taylor polynomial for f about x equals 0. So a couple things to note here. This converges. That's what I'm talking about when I say they might reference the radius or interval of convergence. So that is a reference to it, but it's not actually significant to what we're actually doing here. We are just looking for the fourth degree Taylor. So I'm going to put it down as P sub 4 of x. That's what we're looking for here. And you can also note that your center is 0, which is essentially telling us this is a Maclaurin, but they've referenced it as a Taylor centered at 0. That's totally fine. So what they did give us is they gave us an initial value, f of 0 equals 2, and then they gave us a derivative. So f of 0 equals 2 and f prime of x equals f of x plus 1. Well, we need to write the Taylor polynomial up to 4 degrees, so we need f of 0 plus the first derivative evaluated at 0 times x, technically over 1 factorial, but we don't necessarily always have to write that, plus the second derivative evaluated at 0 times x squared. I'm not actually putting x minus 0 squared because our center is 0, so I don't actually need to subtract anything from x here. Over 2 factorial plus the third derivative evaluated at 0 times x to the third over 3 factorial plus the fourth derivative evaluated at 0 times x to the fourth over 4 factorial. So now I have 5 terms, but my degree is 4, so I need all 5 terms in order to actually have a degree 4 here. So we've actually found f of 0, that's 2, and we have a derivative. So from there, we're just going to need to find f prime of 0, take the derivative of f prime, get the second derivative, take that derivative again, get a third derivative, take the derivative again, get a fourth derivative. So really you're just going to find a bunch of pieces and plug them all in together to get your final answer here. So I'm just going to make a list. I know I've already written this once, but I like to stay organized. F of 0 is 2. F prime of 0 is f of 0 plus 0 plus 1. F of 0 was 2 plus 1 is 3. As a little sub note, I'm going to do f double prime of x equals, so I'm going to take the derivative of the first derivative to get the second derivative, and we get f prime of x plus 1. That's all we do to get that derivative there. We're just taking the derivative of every term up here. So the derivative of f is just f prime, derivative of x is 1, and then the derivative of 1 is 0, so I don't have 0 there. So f double prime evaluated at 0 is f prime of 0 plus 1, which is 3, like we just calculated, plus 1. So our second derivative evaluated at 0 is 4. Now we need the third derivative. Sorry, I didn't move it over, but it is what it is. The third derivative of f evaluated, or of x, sorry, is the second derivative of x. And we just have a 1 here. So really, the third derivative is equal to the second derivative. So f triple prime of x equals evaluated at 0, f double prime evaluated at 0, which once again is just 4. And the last one is the fourth derivative of x. Well, we're just taking the derivative of the third derivative, which would just be that the fourth derivative is the same as the third derivative. So the fourth derivative evaluated at 0 has to be 4 as well. So, looking at that, now we just go back to p sub 4 of x and plug in all of our pieces. So, 2 plus 3x over 1, you don't necessarily have to write it that way, you can just write 3x, plus 4x squared over 2, you don't have to write it that way, you could just put it as 2, plus 4x to the third over 6. I will put 6 instead of 3 factorial. You can put 3 factorial. Plus 4x to the fourth over 24. I'm just going to go ahead and put 24. If the problem only asks you for the polynomial, great, don't even bother simplifying. If you recognize that they're asking you to do something with it later, maybe take a derivative, an integral, then maybe simplify so that it'll be easier to work with later. So that would be your final answer for that question, working through each of those pieces right there. So really you're just finding derivatives and their values, and then plugging them into that formula where each term comes from a derivative evaluated along the line. So moving on to our second example here, we have the third degree Taylor polynomial about x equals 0 of ln 1 minus x is, and they just want us to find that. So this one's a little bit more straightforward. Our center once again is 0, so it's another Maclaurin one essentially. Our function here is ln 1 minus x. So really what we need is p sub 3 of x is what? Well, really that is f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x to the third over 3 factorial. That's me just applying the Taylor polynomial formula. Now it's basically just a puzzle. Find all the pieces and put the pieces together. So f of 0, plug in 0 to that, and you get ln of 1 minus 0. That's just ln of 1, which is just 0. Now we need the derivative of f of x. So the derivative of ln of 1 minus x is 1 over 1 minus x, but don't forget the chain. We have a negative x, so the chain would be negative 1. So ultimately, f prime of x is negative 1 over 1 minus x. You could simplify that in other ways, but that's how I'm going to write it. So f prime of 0 is negative 1 over 1 minus 0, which is just negative 1. Next, we need the second derivative of x. So we're taking the derivative of negative 1 over 1 minus x, and now I'm just going to use a power rule. So essentially, this could be rewritten as negative 1 minus x to the negative 1. So drop the power down and subtract, and you would get negative 1 times negative 1 times 1 minus x to the negative 2. Once again, don't forget your chain. So the negative 1 comes from this negative out front. This negative 1 comes from the power. Drop the power to negative 2, and then the chain right there is negative 1. So this simplifies to negative 1, negative, 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 makes a negative still, over 1 minus x squared. So f double prime of 0 is negative 1 over 1 minus 0 squared, which once again is just negative 1. On to our third and final derivative. The third derivative of f is negative 1 times negative 2 times 1 minus x to the negative 3 times negative 1. I know I didn't rewrite it with a negative power here, but you can see it from there. Negative 1 times negative 2 times negative 1 gives me negative 2 over 1 minus x to the third. So f triple prime of 0 is negative 2 over 1 minus 0 to the third, which is just negative 2. So now we have all of our pieces. Let's just go ahead and plug them in. F of 0 is 0, so I'm not even going to bother writing that. F prime of 0 is negative 1, so we have negative x. F double prime of 0 is negative 1, so I'm going to put minus x squared over 2. And f triple prime of 0 is negative 2, so I'm once again going to put minus, but I'll put a 2, x to the third over 6. Once again, you could simplify that if they were asking you to do more with it, but it's just asking you to write it, so that is totally sufficient right there. On to the next. So example 3 says, let p of x equal 3x squared minus 5x to the third plus 7x to the fourth plus 3x to the fifth. That's the fifth degree Taylor polynomial for the function f about x equals 0. The question is, what is the value of f triple prime of 0? So this is asking us to work backwards. They've given us p sub 5 of x, and they want us to find f triple prime of 0. So what we need to think about is the definition. Oh, didn't mean to put a squared on that. The definition of a Taylor polynomial. So I've started that. We have the original function evaluated at 0, the first derivative evaluated at 0 times x over 1, second derivative evaluated at 0 times x squared over 2 factorial, plus the third derivative evaluated at 0 over x to the third, times x to the third over 3 factorial, plus the fourth derivative evaluated at 0 times x to the fourth over 4 factorial. And hopefully you've already realized at this point this could go all the way up. Well, this will go all the way up to the fifth derivative evaluated at 0 times x to the 5 over 5 factorial. That's a sloppy 5. I'm off my edge there. But hopefully you've recognized that we just found what we needed. We needed the third derivative evaluated at 0, and that shows up on the x to the third term. So what I need to do is I need to take my polynomial that they gave me and equate the two and pull out the pieces that I actually need. So from my original formula, we have f triple prime of 0 x to the third over 3 factorial. And we know that that's going to be equal to negative 5 x to the third. The reason for that is because we're taking the x to the third terms and their coefficients have to be equal. So from there, we're able to recognize that the third derivative evaluated at 0 is going to come from these things here. So ultimately, we can get rid of the x to the third things. 3 factorial, I'm going to rewrite as 6. 3 times 2 times 1. So f to the third derivative of f evaluated at 0, finally got it right there, over 6 equals negative 5, and now it's just one simple algebra step. The third derivative of 0 equals negative 30. So we took the original definition, we recognized that it gave us what they were asking for, the third derivative of f evaluated at 0, and we equated it to the actual polynomial that was given. The one way that we can connect them is x to the third shows up on both of these terms. So from there we write just a small equation that contains that, where we can solve for the third derivative evaluated at 0. So that negative 30 right there. Awesome. So that's another way that they could ask a Taylor polynomial question. This is my last example, and it looks at multiple representations and takes you through how they could actually work through a full question where they're asking you several layers throughout the whole problem. So example 4 has a couple parts to it. I'm going to do each part one at a time here. So the question is, let f be a function having derivatives of all orders for all real numbers. Selected values of f and its first 4 derivatives are shown in the table above. So you can see that we have our x's on the left and then all the function and derivative values in here. So it's 5 whole things. So we could get a polynomial of degree 4 if they asked us, because we have up to the 4th derivative here. The first question says, write the second degree Taylor polynomial for f about x equals 0 and use it to approximate f of 0.2. So this will be the first time we've actually done an approximation, but writing the second degree Taylor polynomial should be the exact same process. The one thing to note is A is asking us to look at just this 0 row. They want us to be centered at x equals 0, so we don't need any of these bottom values down here. So p sub 2 of x equals f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial. That's pretty much it. So f of 0, I'm just going to put this over on the side. That's 4. F prime of 0, that's 5. And f double prime of 0, that's negative 1. So now that I have my pieces, I'm just going to plug them all in. F of 0 was once again 4. F prime of 0 was 5. Don't forget your x. F double prime of 0 is negative 1. Notice I wrote my plus sign before I put my minus. Doesn't matter. As long as you have the negative and don't lose it, you're good to go. And there you go. But don't get sidetracked in the middle of the problem. We wrote the second degree Taylor polynomial, but the real question was asking us to approximate f of 0.2. So what we really need to do is say f of 0.2, and we are approximating, so we need the squiggly equal sign, is approximately equal to our second degree polynomial evaluated at 0.2. So all we need to do is plug in 0.2 in for all the x's, and we're good to go. On the BC Calculus exam, you are actually done right here. If you want to type it into a calculator and just get an idea of did you do this right, it's not going to hurt you to do it. So 4 plus 5 times 0.2 minus 0.2 squared divided by 2. It's approximately 4.98. You can type it into a calculator. You can leave it. Either one works. If they're asking you to interpret the number, then it might make more sense for you to actually calculate it rather than just leave it in this format here. So don't just get stuck on writing the polynomials. When they ask you to approximate, you need to actually do so and make sure you use proper notation. So f of 0.2 is approximately equal to your polynomial, which is equal to this value. So your approximation, just to be abundantly clear, is approximately 4.98. Second part of this, I'm still going to need that table, so I'm going to keep that sheet close. It says, let g be a function such that g of x equals f of x to the third. Write the fifth degree Taylor polynomial for g prime, the derivative of g, about x equals 0. So once again, we're around 0, so that's good. So we're going to be using this top row. I guess I didn't need to cross through it. But we're going to be using this top row again. We're not using 1, we're just using 0. But the first thing we need to connect is how g and f are related here. So g equals f of x to the third. So the big connection that we need to make here is what we're actually doing with our x's. So ultimately, what we're doing with these x's is we're saying that f of x is approximately p sub n of x. The x's equate here across the board. So if we say we have f of x to the third, then all we really need to do is change our polynomial's input of x. So it's p sub n of x to the third. Well, we just found the second degree about 0. And I keep forgetting to change that into a minus. Maybe I'll get it right one of these times. But if we want to work towards this, all we really need to do is change our polynomial so that everywhere we have x, we are plugging in x to the third. So 5x turns into 5x to the third minus, finally got it right there, x to the third squared over 2. So I'm going to simplify that. Only one thing to simplify. We have the second degree polynomial of f of x to the third equals 4 plus 5x to the third minus x to the sixth over 2. So now essentially all we've done is we've accounted for that x to the third that they were mentioning for above. So this, we can say, is approximately, I should put the approximate squiggle bars, equal to g of x. Now we want g prime of x. So what we should do is we should just take our derivative here. You can see I skipped over 4 because the derivative of 4 is 0. 5x to the third becomes 15x squared. And x to the sixth over 2 becomes 3x to the fifth. 6 divided by 2 is 3, and then the power just drops down to 5. Ultimately, it wasn't too bad. All we did was we took the polynomial that we had just created, we recognized how it worked with the change to our f that we had. We plugged that into our polynomial, and then we recognized, okay, if that represented f, then it does also represent g, and from there you just take a derivative of the power series itself, of the polynomial itself. So to conclude, we have C. C says write the third degree Taylor polynomial for f about x equals 1. So this is the one problem that is going to ask us to use this bottom row. So once again, be careful with what you're looking at here. So A and B, we use the first row. C is going to use the bottom row there. C says write the third degree Taylor polynomial for f about x equals 1. We're good to go. We just need p sub 3 of x equals f of 1 plus f prime of 1 times not just x, but x minus 1. So that's something important to notice, is that when we change our center, we need to change how we look at x. Plus f double prime of 1 times x minus 1 squared over 2 factorial. And we're only up to a second degree, so I need one more term. F triple prime of 1 times x minus 1 to the third over 3 factorial. And there you go, we have it. But we got to find all the pieces and plug them in. So f of 1 from my table, I'm just going to write it and read it to you, is 8. F prime of 1 from my table is 3. F double prime of 1 from my table is negative 2. And f triple prime of 1 from my table is 3 halves. So one thing to note here, I will bring the table over for this, is we never used this fourth derivative. It's kind of a trick on part B for you to, they want you to think that you need to actually use part B, use f to the fourth derivative of f, and use those values, but you don't actually need it there. So sometimes they put more information than you actually need. So the last step for C is just to plug in all of our pieces. We have 8 plus 3 times x minus 1 minus 2 times x minus 1 squared over 2 factorial plus 3 halves times x minus 1 to the third over 3 factorial. All I did was plug in each of these values here into my equation above, and I didn't even bother simplifying it. I didn't distribute the 3, I didn't simplify the 2's, I didn't simplify this fraction and the factorial here, and I definitely did not expand that polynomial there. So this is totally acceptable, you're good to go once you finish that, and if they don't ask you to approximate anything, that would be your final answer there. So that's a rundown of how to work with some Taylor polynomials in the context of what the AP exam could look like. Feel free to practice them using the resources that I've provided and You can watch the YouTube lessons provided by College Board Online that takes you through some even more in-depth examples of these. Thanks for watching and have a great day.